Welcome to the Explainer. Today, we're talking about the electricity that's literally flowing through the walls around you right now. Alternating current. Now, it seems simple enough, but it's hiding a few secrets that are actually pretty surprising. So let's just dive right in with a puzzle. You look at your appliances and you see that number printed on them, 220 volts, or 120 if you're in the States. But is that number telling you the whole story of what's coming out of your wall outlet? Well, spoiler alert, not even close. Check this out. For a standard 220-volt outlet, all three of these numbers are correct, all at the same time. The voltage physically hits a peak of 311 volts. Its effective value is 220 volts, and its average is a big fat 0. So how is that even possible? Let's untangle this, and we'll start with that 0. Okay, so the first piece of the puzzle is figuring out why a simple average just gives us nothing. And the clue, as you might guess, is in the name itself, alternating current. You see, the current doesn't just flow in one direction. It's constantly changing, moving back and forth in this really smooth wave. So for every single moment it pushes out with positive voltage, it spends an equal amount of time pulling back with negative voltage. Over one complete cycle, those two halves just perfectly cancel each other out. That's why a simple average is always 0 and totally useless if you want to measure its power. Now, you could try to cheat, right? You could just measure the average of the positive half of the wave, and you'd get a number. It's about 64% of the peak. But that's still not the whole picture. It doesn't really tell you about the true power, the actual work that this electricity can do. For that, we need a much smarter way to do the math. So if a simple average is out, how do we find a value that's actually meaningful? Well, the answer is this really clever mathematical trick that lets us find the true, effective power of that constantly changing wave. This whole process is called the root mean square, or RMS. And funnily enough, you actually do the steps in the reverse order of the name. First, you take all the values and you square them. Poof, all the negative numbers are now positive, so our cancellation problem is gone. Then you find the mean. The average of all those new squared values. And finally, you take the square root of that mean to get back to a sensible number. And that's it. And here's why that RMS value is so incredibly useful. It's basically the DC equivalent. What that means is an AC current of 220 volts RMS will produce the exact same amount of heat and do the exact same amount of work as a steady, unchanging 220 volt DC current. It's the number that actually tells you how much power you're getting. And this brings us right back to our original puzzle and solves it beautifully. That 220 volts you see everywhere, that's the RMS value. It's the effective power. And it's derived directly from that physical peak of 311 volts just by dividing by the square root of 2. Mystery solved. Okay, but the story of AC gets even more interesting when we start looking at how different electronic components actually handle all this change. Turns out not everything can keep up with AC's constant back and forth. A simple resistor, well, it's simple. The current and voltage rise and fall together, perfectly locked in step. We say they're in phase. But inductors and capacitors, they throw a wrench in the works. They create a time delay. An inductor makes the current lag behind the voltage, while a capacitor does the opposite. It makes the current lead the voltage. They're constantly pushing the timing out of sync. So what you have in pretty much any real-world AC circuit is this constant battle, this tug of war. The inductor is trying to hold the current back, the capacitor is trying to push it forward, and the resistor is just trying to slow the whole thing down. This combined total opposition to the current has a special name. We call it impedance. Now, this internal fight, it sounds pretty inefficient, doesn't it? But what if we could actually harness it? What if we could make these opposing forces cancel each other out perfectly? This is the key question. When that time delay from the inductor is precisely balanced by the time advance from the capacitor, something really incredible happens in the circuit. At one and only one specific frequency, what we call the resonant frequency, their opposing forces completely neutralize each other. It's like they call a truce. And the circuit's total impedance, it suddenly just plummets, leaving only the simple resistance. The fight is over. So with all that opposition gone, what do you think happens to the current? It surges. With the impedance at an absolute minimum, the current flowing through that circuit shoots up to its maximum possible value for that voltage. And we call this condition resonance. By perfectly balancing the properties of the inductor and the capacitor, we've basically created a circuit that is extremely, extremely receptive to one single frequency, and one frequency alone. And this isn't just some theory from a textbook, it's the technology that makes pretty much all wireless communication possible. When you turn the dial on a radio, you're actually just changing the properties of a capacitor or an inductor. You're searching for the exact resonant frequency that matches the station you want to hear, which allows that one signal to surge through while all the others are just ignored. So we started with a simple puzzle about the voltage in your wall, and we ended up at this fundamental principle of resonance. It's a great reminder that sometimes efficiency isn't about eliminating opposition, but about finding that one perfect balance point. It's what lets us tune a radio, and it makes you wonder what other complex systems, whether in technology or just out there in nature, rely on finding their own perfect frequency to really work their magic.